Consider a ring of radius A formed by a thin wire carrying a current I. The axis of the ring is taken along the x-axis as shown in figure. Suppose that we want to find the magnetic field at a point P on the axis of the ring at a distance x from the center of the ring. Let the position vector of point P with respect to an element of wire vector dl be vector r. The contribution vector dB to the magnetic field at point P due to the element I into vector dl has a direction of I into vector dl into vector r, perpendicular to the plane made by vector dl and vector r. This field vector dB can be resolved into two components, viz. a component dB cos phi parallel to the x-axis and a component dB phi perpendicular to the x-axis. The total field is a vector sum of the elemental fields vector dB contributed by different elements of the entire ring. It is not difficult to see that, corresponding to each component like dB sin phi, which are directed perpendicular to the x-axis due to a specific ring element, an equal and oppositely directed component will be contributed by its diametrically opposite ring element. Therefore, in taking the vector sum, the net value of the component of the field perpendicular to the axis will be 0. It can also be seen that the axial components dB cos phi add to each other. Now, dBx is equal to modulus vector dB into cos phi, and modulus of vector dB is equal to modulus of mu 0 upon 4 pi into I into vector dl cross to r upon r cube. But vector dl is perpendicular to vector r. Therefore, modulus of vector dB is equal to mu 0 I upon 4 pi into dl upon r square. Therefore, dBx is equal to mu 0 into I upon 4 pi into dl upon r square into cos phi. Therefore, Bx is equal to mu 0 I upon 4 pi r square into cos phi into integral dl. Therefore, Bx is equal to mu 0 I upon 4 pi r square into cos phi into 2 pi a. From figure cos phi is equal to a upon r. That is equal to a upon a square plus x square raised to half. And r square is equal to a square plus x square. Using equations and in the equation we get Bx is equal to mu 0 into I into a square upon 2 into a square plus x square raised to 3 upon 2. Note that the direction of the magnetic field is along the axis of the ring. We have selected the x-axis in this direction. A special case. Magnitude of the field at the center of the ring is obtained by putting x is equal to 0 in the equation. Thus, at the center of the ring, vector B is equal to mu 0 into I upon 2a into I cat vector. If the ring is of n closely wound turns of wire, in the general case, vector Bx is equal to mu 0 into n into I into a square upon 2a square plus x square raised to 3 upon 2 into I cat vector, and at its center, vector B is equal to mu 0 into n into I upon 2a into I cat vector.